So, okay. Hello, everybody. My name is Dietmar Kuhl. I work at Bloomberg. And the first thing I want to mention, as some other have mentioned in their talks as well, I'm by no means an expert on that stuff. I'm a dude. I've played with that. If you expect me to talk about GPU stuff, sorry, won't come. I think I know some stuff of that, but I also see some people in here whom I expect actually know more about that stuff than I do. I hope they would at best correct me where I'm entirely wrong, and otherwise present next time to actually tell people how to do it properly. So what I started out over here is basically something which I did for a long time for other things as well, and that is I'm interested in how does a standard library, how does C++ work actually under the covers. So let's say I/O streams, everybody knows about I/O streams, everybody has used it, but hardly anybody knows how it is implemented. Implementing it is actually kind of interesting, and you learn a lot about that stuff. Likewise with parallel algorithms. I would like to know, how do they actually work? Can I just knock it up and do it? The other part of that, aside from looking under it is the standard library does provide a number of parallel algorithms, but it is not necessarily complete. And sometimes it may be necessary or useful to implement your own parallel algorithm, and you may or may not be able to leverage what exists. So maybe it's useful to know or to get an idea of what can be done to actually make things work. That's roughly what I'm going to talk about. And my implementation, I hope you're not too disappointed about that, won't meet what the standard library does. I think it gets reasonably well, but not as fast as the standard library does. Okay, so what I'm going to talk about is actually a relatively straightforward parallel algorithm, not super straightforward. I'm not just talking about something like the reduce, which is massively parallel, but rather inclusive scan, which is not as obviously concurrently, but it's actually one of the important building blocks of other parallel algorithms so that you don't have to do all that leverage for these things. I basically start off with a version from a textbook from Introduction to Algorithms and work on that to basically make it work. I want to provide versions using a few concurrency systems which are not standard, or at least not ISO standard as part of C++ standard, like an OpenMP and set building blocks. And then I built also a version which entirely builds just on C++ standard library. So let's start off with the simple thing, and that is what is inclusive scan. In the standard library, it used to be available as partial sum, or it's still available as partial sum, but the parallel version and the new version is inclusive scan. What it does is basically just computes the sum of the elements, and unlike accumulate, it also stores all the intermediate values. So over here is the input and the output. Let's go and look at how it is computed. It's very simple. For the first element, we just copy. For the next one, we basically take the previous one and add the next one, and we keep doing that. And if you look at that, it's kind of, all right, each value depends on the one before. That's slightly annoying. We cannot just compute things nicely in parallel. We need to have the values before. Before going into the parallel version, the sequential version is really, really straightforward. Here's a simple implementation. It's basically split into two parts to get all the necessary overloads. The first version is basically just taking an input range and output range in operation and just computes, and basically all it does is it delegates to different algorithms. That's fairly common practice. You get, if you went to Connor's talk, he said, all right, all these algorithms are actually effectively just reduced. This is a similar case over here. So, we delegate inclusive scan of one version to a different version. And the other one just does the computation. The key difference is we have an initial value and we can just deal with the initial value. So this is basically, yeah, okay, we have a special case for, well, if there's nothing to do, then we don't do that, and otherwise we now have an initial value we can work off. But this is the reason, the initial value is the cause of a lot of plus ones in some of my code. To basically say, all right, we set that off and we pass the initial value or the first value in the back as the initial value, so we don't need to deal with that. And then in the other algorithm, it just iterates over that. Okay, that doesn't look super suitable for parallelization. And indeed, when you do parallelize this algorithm, you actually do end up doing more work. That is, if that were a sequential approach, you would actually spend more time. However, because things are parallel and we can actually use more processors to do more work, we may bring down the overall time by actually spending instead more work. This is a basic idea. So the rough idea is, we decompose the algorithm, the sequences into two, and keep doing that, and we compute basically the initial values of what we need to store of intermediate steps, and then we just distribute that. Or to write it differently, so we can compute, if we have the middle, let's say, we have the middle value of the initial sum, we can basically fill the two sequences in parallel. This works nicely. And then obviously if you do that instead of doing it with just 2, we can do that with 4 or 8 or 16. Depending on how many processes we have, we can do that nicely in parallel. So all we need to achieve is compute things quickly, and we can do that in log n time. This is effectively multiple accumulates running, and then we can also in log n time distribute things. So all in all, the algorithm spends O of n work, but actually just O of log n time, assuming we have infinite processes. Okay, so the implementation or the original algorithm of that, I've taken from this book. When I mention the name, nobody recognizes it. I hope the picture makes it recognized. Well, most people hopefully have seen that. I know it when it had still just 3 authors, but I don't think there was a parallel algorithm in there. And this is how the algorithm looks over there. There are 2 algorithms being called, pscan up, which basically computes the intermediate sums, and then pscan down, which distributes them. And this is basically the initial algorithm, which basically just orchestrates that. So implementing that algorithm, so the first step is actually taking the algorithm and translating it to C++. Well, this is relatively straightforward. This is actually just the same steps, and it's not super interesting. It gets a little bit more interesting if you look at something like pscan up, because there's actually concurrency happening. So this pigeon language over here basically has a spawn operation to kick off a thread. So basically the spawn executes concurrently to the non-spawn version, and sync, we basically expect both of the other threads which are spawned to come back. And after sync, we have basically the results of both of these in place. So translating that to C++ is also fairly straightforward, and I'm using something which was sort of being removed and not being removed, std async. So for a while, people told me, yeah, no, std async is the way to go. If you want to do things in parallel, use std async. And then they go, well, that doesn't quite have the right interface. It produces the wrong future, as far as I understand it. But fine. Let's use std async. And we basically kick off a thread by std async, and we just wait for it. And then the other thing processes the same thing. The way it works effectively is it basically stores things over here in this temp variable, which is basically an intermediate stage, and then actually distributes things. The algorithm, if you look at it over here, actually has these 2 internal arrays, y and t, to basically store the intermediate stage. It would be nice not to have intermediate memory, but I think to make the algorithm actually effective, there will be some extra memory needed. Okay, so this is one direction. The other direction is actually just the same thing. It basically just decomposes everything nicely and spawns threads and then syncs. And again, we do that with async and wait, and that should be fine. So basically, this is a literal translation of the algorithm. If anybody has experience with taking a textbook and translating an algorithm and trying to run it, you would not expect it to run particularly fast, I guess. So let's see how bad that runs. First off, it's important to mention on what kind of machine I'm executing things. the stuff is executed on a machine that actually has quite a number of cores, 64 cores. It's a Knight's Landing machine. They're all on one chip. It has 16 gigs of relatively fast access memory on that chip, in addition to whatever caches it has. So it has basically, and then it's 4 times hyper-threaded. So if you run a parallel program over there, standard libraries typically report that it has 256 hardware threads. So it should be actually massively faster. Now we all know that memory is a contention, and they actually make running this thing on, let's say, just an inclusive scan on integers actually doesn't give a lot of benefit, at least not as massive as I would have hoped for. But so I basically compute something which is a made-up problem. Let's say we compute a sequence of 4 times 4 float matrices just computed against each other. There are more interesting use cases which are just harder to explain. And I think people understand how a matrix multiplication looks like. It actually does a number of operations on that. It's just intended to not make it entirely memory bound. And then I will show graphs, and low is good, high is bad. So all of the graphs show something like that. You see maybe you basically see at the bottom a light blue line. This is the benchmark. This is what I mean with benchmark. This is a sequential version. And the parallel version we just implemented is that orange, is that violet line. That is not good. So we just did some work and we made it all nice and parallel and probably used quite a bit of CPU power, and it got something in the order of 1,500 times slower. We want to have it a lot faster. At the bottom, you see a number of other guys. I will explain those. So the first step is the algorithm actually creates a lot of tiny tasks. For each element, it basically effectively it creates, well, not for all of them, but for half of the elements, it basically creates at least actually it's more than that. It creates a lot of these async futures. So a huge amount of futures generated. We don't necessarily need to do that. Once we actually have a range which is reasonably small, we can reasonably decide, let's stop trying to do something concurrently over here, and we just do it sequentially on that level, and then we execute these in parallel. So effectively, we change the algorithm. The main change over here is just on that a bolded line to basically say instead of we stop at 1, when we have moved down to the smallest bit, we stop at some min size, whatever min size is. And I basically tried with a few variations. And then once we have reached that level, we basically just do accumulate, because the first guy is just computing the sums of subsections. And likewise, in the second case, because now we cannot actually we need to basically change these things in lockstep, because otherwise we wouldn't compute all the sums we need. This guy, we need to actually use the same blocking to basically figure out what are the values we then need to distribute. And so we do inclusive scans on the subranges. And that improves things quite a lot. As you could see from that graph, this is all at the bottom over here. So with that, the computation is, let's say, only 200 times slower. Okay, well, okay, I'm not going to stop here. That would be bad, right? So the thing is, over here, I'm just using async, which is something which is nicely provided by the standard library. But actually, I just need to get some jobs scheduled. And async is certainly one way to do that. There are other ways to do it. And one way we could do is, let's say, I use thread building blocks. The reason I use thread building blocks is basically just I know that for a longer time. There are other libraries which do something very similar in that space. I just haven't used them. So in thread building blocks, there's something like a task group. A task group basically aggregates jobs. You stick jobs in, and eventually just wait for all the jobs to finish. And this is basically the equivalent of the synchronization thing. Task group run is the same thing as basically schedule that job and run it elsewhere. We actually didn't do a massive change in the structure of that thing. Instead of using async in the future, I use a task group and the wait thing. Not dramatic. And the same over here. I just use the task group again, run a job, and the job is just the same as before. And then I just wait on the aggregation of these things. And hopefully this makes things better. And actually it does. So I'm not excluding the possibility, and it's actually potentially quite likely that I've just misused async, and I correctly used the task groups to make it work, but the task group made it really easy to make that right. So over here you can see the blue line. This is basically the flat line. This is it's just the benchmarking the corresponding sizes. So basically on the going from left to right is basically smaller sequences up to bigger sequences. And basically the blue line is doing it all sequentially. So in the beginning, I don't make any benefit, but once the sequences become big enough, there is at least an overall benefit. So that's a good start. There is actually a potential to actually get responses faster. So the next stage of that is to say, well, what if we actually, instead of reformulate it as kind of, which is natural for a nice divide and conquer algorithm, instead of decomposing it basically into a recursive hierarchy, or where we basically, instead of doing recursion, every time we recurse, or we don't really recurse, but we actually just start another job. Instead of doing that, we could actually turn the algorithm a little bit around and basically make it iterative. The nice thing of doing that is that tools like OpenMP which can parallelize loops. So if you actually have a nice loop which does which needs to be parallelized, we would be in a position to use that. Also at building blocks also as a loop constructed, which make it easier. The standard library algorithms, unfortunately not so much, at least not on that level. There is obviously something like a parallel for each, but the parallel for each actually chops things up internally without your control. And basically you don't know where did it split. But we would like to know, all right, I've already chunked things up and I want to schedule these things. So the standard library didn't really help me as much over there. But anyway, let's turn the algorithm into an inclusive scan and make that basically an iterative approach. It doesn't fit on one slide. So I basically have these things to basically say it consists of 4 stages. The first stage is let's set up some auxiliary stuff, which is basically just some memory. Then we compute the sum of subsequences. Then instead of actually recursing on the thing, I just use an inclusive scan effectively to compute the actual elements we need. So basically, first guy is just computing the elements of the ranges concurrently. Then we do an inclusive scan to compute the things that could be parallel as well, but I don't think we have actually big enough computers for that to make it worthwhile to make that parallel. And then we combine them again. So the auxiliary stuff is basically just a number of type defs and the intermediate storage. The intermediate storage over here, I'm a little bit more careful about the value type I get out of here. So if one part of that gibbery is all just computing the value type. Once I get the value type, I make the assumption that I actually don't know much about that value type. For example, I don't necessarily assume that it can be default constructed. So I just create a container where I can stick things in which cannot be default constructed, and I can just set them later. The normal approach in other generic code is you typically wait until you have the object and you stick it in the container at that point in time. That doesn't work in parallel particularly well because you never know which thread is ready when. So basically distributing that stuff ahead of time and creating space is kind of necessary. Okay, so that's just a setup. Computing the sums of subsequences, well, all we do over here is in principle, this is obviously a sequential version of the stuff. We just compute the sums of the subsequences. There is a -1 highlighted. The reason for that is for the last chunk, we actually don't need to compute the sum anymore. We only need this initial value. So we don't need to deal with the end condition that there's basically a range which may not be the right size. We only deal with the chunks up to that thing. They have all the same size. That makes that loop relatively easy. And all it does is it basically uses the integer and computes things. This loop is nicely accessible to OpenMP. If we want to get that parallel, we just slop OpenMP, pragma OpenMP parallel 4 on top of it. And then OpenMP will actually nicely go, yep, I can parallelize that. We can do pretty much the same as I did before with the task group to basically say, all right, I can actually schedule these things in parallel as well using a task group. And Strat Building Blocks has an for each construct that looks like that, which actually basically provides a function with an index and executes these things in parallel. And that's quite nice because it promises that each index is, well, it somehow parallelizes on the indices. It probably kicks them off in parallel in some shape or form. They don't really document entirely how that is done, but it seems to be nicely parallel. So we can do that. And to do something similar like that in a kind of for each algorithm, well, there's something slightly annoying in there, and that is to actually store things into that intermediate array, I actually would like to get an index. I would like to know the chunk number. And yeah, I can implement that in the algorithm, but then the algorithm comes somewhat convoluted. So I basically came up with the idea to say, all right, I actually have a for each, and I do the for each subrange. And what that thing produces is, you can basically see it from the signature of the green lambda. It produces an index and a begin and end of the subrange. So you basically get told, all right, this is the ith subrange, and this is what the range actually is. And I will later show how that is implemented. So this is basically chunking up the intermediate initial computation. That's relatively straightforward. Then the intermediate over here, I actually should have changed partial sum over here to inclusive scan, but it doesn't matter, it's just the same thing. It's just a sequential version of let's compute things in that intermediate array. One thing which is slightly annoying over here is the intermediate array actually is optionals. They would all be populated by the time we get here, but we need to have that funny, I didn't highlight that, we need to dereference the elements we get to get the actual value of the optional rather than the optional. We want to apply the operation which we get to the actual elements. And then the other end is more of the same. We basically, again, go over the entire sequence. This time, we need to process all sequences. So there's actually special handling of the end sequence, of the end chunk. So most of the chunks are equal sized, but the last one may have a smaller size. This is a reason for the green stuff at the back. And then the next stage is to basically compute an initial value of the inclusive scan, so that from then on everything works nicely, and I do the same thing as I did with the initial value. Basically, right, I take the value I get from the intermediate thing. This is the star temp of the I-1 thingy, together with the current position, and basically compute that. There's a little bit of jiggering about with the iterators over here, because I actually have two sequences which are parallel, the true sequence where I need to write things to, and the source sequence where I get things from. So I basically need to compute the start position twice, and that happens in both of these cases. But this is relatively straightforward translation of the original algorithm. So, and then again, making that parallel, because that is now a loop, we can make it parallel with OpenMP, or with task groups, or with parallel 4, or again, although this becomes again a little bit more complicated, with the for each subrange. And the for each subrange would basically execute things. And there's something in there which I didn't mention before. I basically pretend I know what an executor is. The standard committee is in discussions what an executor is since probably 10 years. And hopefully we'll discuss only another 2 years or so we get into 23 and we actually get these things into the standard library. It would be really nice. but all I need over here is something, I assume this thing has an operation execute, and I execute a function. Okay, so with that, I have implementations, and to basically run things in parallel, and this is how the graph looks like. Unfortunately, there's a massive outlier at the start. I don't know where that came from and what that does. And basically, it hides a little bit what's going on over there. So basically, this is the same graph with just some of the top stuff cut off to make it look a little bit nicer. So one of the green one, actually became slower. There's no surprise. This is actually basically the sequential algorithm. I don't know why it is actually kind of the same speed at the beginning, roughly. It's a little bit above, but actually you don't even see it in for the first couple of sequences. I guess it is, the reason for that is most of the stuff is in the end still just memory access, and it just gets away with accessing things in cache, and it doesn't really matter that much that we run over things twice. But I don't know why it only pops up later. The other ones are the yellow one, which does best. This is why part of the reason why I'm interested in OpenMP is actually the OpenMP implementation. That gets parallelizes things over here fastest, and it gets a bigger speed up. The other ones are the blue one, the red one, which goes down as is using the thread building blocks version, and the violet one is, and this must be the violet one is using the thread building blocks for each. The executor versions are not there. I first want to explain how they work to actually show them. Okay, so this is actually quite a bit of speed up on that workload at least. Okay, so the algorithm which I'm kind of missing from the standard library so far, and maybe we get something like that to help implementing other parallel algorithms, is something like for each subrange. The idea for each subrange, as I mentioned, is basically we basically produce an index of the current range, and we basically also say this is the begin and the end of the range. I think that's a quite reasonable interface for something if you want to implement parallel algorithms. Over here is a complete implementation of that. It starts off as well, if there's nothing to do, it doesn't do anything. It uses a latch to basically determine when we are done. So the idea of a latch is you basically initialize it once. It's once use thingy. You initialize it with how many things you expect to arrive. And basically once you have people calling arrive on that thing, anybody who's waiting or trying to wait on that latch is let through. If you basically wait before everybody has arrived, you basically wait and get blocked over there. So basically, the latch is just saying, right, we expect that number of workloads to be finished. This is actually, it's my own implementation, but there's latch coming. There's latch definitely in the standard C++ library. When I did that at some point, I just didn't have it available. So the other part is basically the execute. I already mentioned that I basically assume executors have an interface which says execute, and they get one function object. The standard library or the parallelization guys are discussing what kind of variations on execute we want to have. This interface is actually geared only towards running things on a CPU. But once people actually want to run things on a GPU as well, they want more something like batch execute thingy as well. And but unfortunately, the entire discussion around how the executor actually looks like exactly is blocking the availability of at least something simple. Okay, there's one thing I found actually in production code. This is not production code, but I'm also using latches in what I do in a day-to-day work. And we basically had scheduled and queued things, function objects, into some kind of thread queue, and that got full, and the function object got dropped. But people didn't expect that to happen. But once the function object got dropped, the arrive inside the function object, which may have been called, was not called. So there was basically a leak, and basically we had a problem of the latch blocking indefinitely because things didn't arrive. And this is the idea of the latch arriver over here. Basically, in the Lambda function I pass in, I capture a latch arriver. Even if that function object gets dropped on the floor without ever being executed, the arriver will be destroyed. And the arriver in its destructor actually calls arrive. So there's no kind of leak of people expected to arrive. That's a tool which probably would be also nice to have as a complementary for latches, possibly for how the other guy's called, for barriers as well. So to basically just say, right, we have a safe way to arrive or whatever else we need. Okay, and then inside this thing, all it does is it basically calls a function object. The function object is the parameter. Should have highlighted that to basically say what is being executed. And this is basically executed once in a loop where we actually deal with equally sized sequences, and then the last guy gets executed independently because the last chunk may be smaller, so we don't have to special case inside the loop. So this is basically the for each range thing. It hinges on having an executor. So far the things which is missing is OpenMP and thread building blocks have nice task schedulers. They actually kind of know how we schedule tasks. I don't know how OpenMP does it under the hood. They must have something like a task scheduler. Thread building blocks does have a task scheduler, definitely, and they use apparently something like a job stealing scheduler, which is very good for certain workloads. I don't think this workload actually is particularly geared towards the task the job stealing thing, because actually the tasks themselves don't enqueue jobs again. It's basically all just enqueued from the top level rather than the tasks enqueuing things themselves, and the job stealing stuff benefits from basically having a deck where the task itself pushes to the back and consumes directly from there, and it normally doesn't have any contention on that one, whereas others, the job stealing guys would look at the other end. Over here the workload is, well, all jobs just come into the system to start with. There's no local processing. Okay, so but the missing bit is how do we actually schedule this thing? And let's create a really simple executor just to get the idea of what an executor does. And that is, this executor actually doesn't do things concurrently. It just schedules a job on the same thread. If that blocks, there's a little bit of a problem, which is, however, actually an interesting aspect as well. Because actually, if you have an algorithm which blocks if you give it just one thread and deadlocks, the algorithm probably wants to be implemented differently. So this guy basically just, all it does is whenever execute is called, it just executes the function object, and then it returns. This is not particularly interesting, but should be an valid implementation. And then for the other guy is, well, we actually probably want to have a thread pool. This is a simple implementation of a thread pool. I just put it on to basically A for completeness, and then there's some talking points about it. One of them is enqueue JThreads, which is basically just joining threads. All they do is, unlike the stud threads, stud JThread basically joins when being destroyed. For the other guys, you basically always need to make sure you join them. I didn't have an implementation of JThread available as well, so I'm not using a stop token. Instead, I have just a Boolean flag, which is checked once my thread pool should stop. And the other interesting bit is, over here it says function. This function I'm using over here is not stud function. The reason it's not stud function is the arriver I have is kind of not really copyable. I could make it copyable, but then I would need to have reference counting around it. It's only movable. And stud function, as we have in the standard library, is unfortunately not for function objects which are move only. So basically, stud function, if you try to copy or move a stud function, it basically, or in general, actually, it needs to have a copyable function object. but it's reasonably easy to create a function object which is only requires move construction. Okay, so once I have that, there are a few interesting operations. I'm not going to go over all the operations because most of them are boring. The first one is we just create threads. So the thread pool, I do a lock at the start, create all the threads, and then let it go. The reason for that is if you actually have a thread pool and you start using it while it is still being constructed, there may be some funny effects of whatever your pool does under the hood. So I didn't want that. So I basically just create them and kick things off. And creating threads basically just amounts to, right, I create a thread in my pool and I give it work. Scheduling something, there's nothing magic in here at all. You basically block the queue and place a function object, and then we signal in case any thread is waiting to execute things. During normal execution, hopefully we don't need to signal, but whatever. And then the other side is the work. The work is a little bit more complicated because you need a little bit faff around. The first thing is to basically, well, potentially wait if something is on, and I need a unique lock to actually use wait. And then actually the next step is to extract the function object. And the slight pitfall, which is however really quickly noticed, is to actually keep the lock while executing the function. Obviously you need to first release the lock and then execute the function because otherwise you kill all the concurrency. Okay, so this is straightforward. And then based on that we can actually create a really, a fairly simple pool executor. It basically just takes the pool, kicks one of these things up, and every time it calls execute, it just sticks the function into that pool. The executor design at the moment assumes that executors are efficiently copyable. That is, may or may not be the, well, it needs to be the case. There could be other designs where you actually have the executor keep it as a reference, but the design in the standard library is executors are lightweight and you just copy them. Over here, I'm just create this executor and keep a shared pointer to the thread pool. There could also be a design where you basically keep one thread pool per program sitting somewhere, and you keep that. This is, I don't have a huge amount of experience what is the right approach over there. This is part of the reason why I would like people who actually understand that stuff to implement executors so I can just use them. Okay, and then, yeah, this is basically all that goes into implementing an executor. And then I get a graph which looks like that. Annoyingly, at the beginning, again, it makes things a lot slower. So I basically, before I get effective with my implementation, I need to have a minimal size. So I cut off some of that stuff to make it actually more visible. The green stuff is still the sequential executor. So we would expect that to be actually slower, about half as slow as the sequential version because it runs over the sequence twice. And that is basically nearly, well, it's a little bit better, but otherwise achieved. And then the various executors, which I actually show over here, is basically the pool executor, which I just had described as the yellow version. I didn't want to actually add the entire details for an executor which does it with multiple pools, but this is basically all it does is the executor, it uses the same thread pool as before, but splits up the threads kind of evenly between n number of pools, and the executor just goes over them, and basically every time it enqueues a job, it goes to the next one. This would be which one is that? This is the red version, which is kind of nice. I did try to create a job stealing executor myself, but I entirely failed, I think. Well, I didn't entirely fail. This is this is one of the version, and the last one, the gray version, is basically using the task group from thread building blocks again. The interesting bit over there is this thread building block version. I would have expected to be better, but this basically the reason it starts getting good or reasonable relatively late must be in the algorithm. So there's still things in how do I actually implement the algorithm properly, which should make it hopefully better. Okay, with all that said, let's go to how we actually do that. And this is actually a little bit fast, but this is getting to the end. But so the way we actually want to use inclusive scan is none of that stuff. The entire implementation I showed, I think, is relatively complicated. It's certainly more complicated than I would like it to be. I would like to have just an inclusive scan and say, yeah, just execute it, please. And the standard library already has that. This is basically, I just used an algorithm to show what kind of steps I think you need to go to if you want to implement a different algorithm. In practice, we want to use inclusive scan with either PAR, which is basically the execution policy to say execute things concurrently on different threads. And you promise that your element access functions on whatever use iterate with function objects can be executed without deadlocking. Or we want to use PAR unseek. This is basically the version where you go, well, not only are the things thread safe, but you can actually execute multiple of these things kind of on the same thread. This is for something like to use SIMD operations or schedule things on a GPU-like thing, where actually the same thread may execute multiple things. So you cannot even have a lock inside any of these guys. And then inclusive scan seek is the interesting case where you go, well, let's try out before going anything concurrently, actually try whether the algorithm works in sequence. This is, by the way, one of the things I didn't mention so far. While implementing all of these things, the first implementation I had for all of these guys was using a sequential algorithm. And also the next step is, all right, I use chunks. Using big chunks in parallel settings may cause problems, but first I tried with tiny chunks, let's say 4 elements per chunk. So you basically make sure that the chunking business works. If you use 8,000 as a chunk, and you try in your test cases with 100 elements, you never get into the chunking. So you basically want to make sure that you hit things, at least during development, with reasonably small things. Okay, so all that said, the parallel version, I do the same benchmarking with the parallel version. The violet thing over here was the best algorithm I came up with. The green version is obviously the sequential one, and then the yellow is the PAR, and the red is the PAR unseek. The reason, I'm not entirely sure why the PAR unseek is actually relatively consistently faster, because I don't think on that system the algorithms actually have a lot of opportunity to take advantage of anything to make it faster over there, but apparently they did. Okay, so this is pretty much what I wanted to talk about. And so the conclusions I get from that is the parallel algorithms actually do speed things up, at least once you have large workloads. On tiny workloads, they probably don't. And that's even true if you don't just have massively parallel algorithms, but basically something like there's a dependency between elements as in intrusive scan. And then the other part is, although I didn't achieve the standard library thing, I think the implementation of parallel algorithms isn't magic either. We can entirely do it, and if we want to or need to implement a parallel algorithm, we can do that. However, this is my experience not just with parallel algorithms, but with algorithms from books in general. The algorithm actually needs some work to actually make it worthwhile and be effective. So before you actually arrive at a good implementation, you typically need to benchmark and verify that actually your algorithm is good. If you just go, yeah, let's take that algorithm and it says in the book it's good, and then you run it, you will probably get a slow implementation. And then the other thing is, all of that would be, I think, easier if we had decent thread pools. But in any case, you would want to use the standard C++ library versions of algorithms which are there. And the nice thing is, if you're already using algorithms, making them parallel just amounts to plunking in an execution policy, and try it with that. Okay, thank you very much. So, any questions or any discussions, comments? Yes?
Just curious, what is Bloomberg actually using to parallelize the backend?
Oh, to parallelize the backend? I largely don't, sorry, thanks. So the question is, what is Bloomberg actually using to parallelize the backend? The answer to that is, I don't know. I work in one particular area of Bloomberg, which is the data distribution, which is fairly concurrent, but we don't use any parallel algorithms because our workloads are typically, all right, here is one price and we need to process that through changes. And over there, we do use thread pools in some shape or form and message passing and all of that, but none of that stuff, no parallel algorithms or something. Okay. Anything else? All right. Thank you very much.
Sorry. In the constructor of the thread pool,
yes.
you take a lock on the mutex. Can you please explain again why?
Okay, the reason I take the lock on the mutex is I want the threads all be started before I start processing anything else. If you do not take the lock, you may already have a partially working thread pool, which, if you enqueue things ahead of time, possibly from elsewhere, starts running. And I didn't want to do that. This is roughly things. Although, yeah, how do I get hold of the construction thingy?
I thought the constructor can only be run by one thread. And that must be the first
yeah.
thing to do anything else. I don't understand.
Yeah, okay, you're right. Maybe I don't need that mutex. It doesn't harm either. But it's basically just doing startup. The actually busy part is scheduling things. Okay?
Just a question. For which number of data of items is async operations are better than the standard one?
You mean right at the beginning?
Yeah.
So going all the way back to, you mean, when does that graph hit things? I didn't bother running it beyond that size because it already took ages. So this is a relative performance. So it still takes 3,500 times, I think, longer than the sequential version. And the sequential version already starts running lengthy. So it may eventually cut down, but I don't know at which size that would happen. I got bored of waiting.
I guess my understanding of async, it creates a new thread every time. Instead of having a thread,
yes.
This is very expensive. But
okay.
If the site is very big, then you have a creation of
yes.
thread a lot of time, then it's like
yes.
having a thread pool.
So the comment is, the understanding is that async basically creates a different thread every time.
Yes.
I would hope that async doesn't do that, but that async actually under the hood keeps a thread pool.
I recently discovered that thing.
And basically pulls out a thread and runs that. At least that would be a sensible implementation of that. But even so, even if it did that, I would expect it to be relatively slow because you create a future for every individual object over here. There's no chunking happening. And I think chunking is essential to avoid communication for tiny workloads eventually. Okay? Yeah. Okay, so the question is, which compiler did I actually use, or which system did I use for the last standard library stuff? At the moment, I actually only have access to a standard library implementation for the parallel algorithms from libc.c++. I don't know whether any other compiler actually ships the parallel algorithms yet, or at least I don't have access to it. I think Microsoft's compiler is shipping, but I don't have Microsoft's compiler on my machine. Okay? Thank you.